At this year's 2018 Pyeongchang Winter Olympics, elite figure skaters were able to once again exhibit impressive feats of athleticism that had viewers in awe all around the world. How were these Olympians able to perfectly execute such difficult jumps and spins on ice while still being able to make it look so effortless and elegant? To answer this question, we must study different fundamental physics concepts such as Newton's laws of motion and conservation of angular momentum. Let's start off by talking about how a figure skater is able to glide across the ice. This is easy to do because of the very low amount of friction that exists between the two surfaces, the ice and the steel blade. But firstly, what is friction? Friction is the force that resists the motion of one object moving relative to another. The coefficient of friction, represented by Greek letter mu, depends on the materials that make up the two objects and signifies how easily one object moves in relationship to another. As you can see in this chart, the coefficient of friction is very low between ice and steel in comparison to, say, rubber and concrete. Keep in mind that some friction must exist because according to Newton's first law of motion, an object in motion stays in motion with the same speed and in the same direction unless acted upon by an unbalanced force. If no frictional force existed, figure skaters will not slow down when they stop stroking. However, physicists still continue to debate why ice has such a low coefficient of friction. While the majority agree ice's slipperiness is caused by a really thin layer of water on top of the ice, they are not really sure how it forms. Currently, there are two prevailing theories. First is the pressure melting theory. Water is unique in that when it freezes, it is less dense as a solid than as a liquid. Therefore, an increase in pressure leads to a lower melting point, and many have hypothesized that pressure due to one's weight on top of a thin blade causes the top layer of ice to melt. However, further research and calculations have shown that the amount of pressure required is so high that even an elephant on high heels wouldn't be able to achieve the pressure needed. The other well-known theory is the frictional heating theory, which suggests that the heat produced from the friction between the two objects is able to melt the ice. But as anyone who has ever skated before will tell you, it is still easy to slip even when simply standing on the ice. In addition to Newton's first law, figure skaters also utilize Newton's third law of motion in order to accelerate across the ice. Newton's third law states that for every action there is an equal and opposite reaction. In skating, when the skater pushes with backwards force on the ice exerts a force in the opposite direction that helps skaters to move forward. This can be seen in my forward crossovers, which consist of two separate pushes which help me to generate speed before my spins and jumps. In addition to this, the conservation of momentum is also utilized when doing jumps and spins. While many complicated elements exist, it is easiest to examine how this principle is taken advantage of in a simple upright scratch spin, shown here. It is commonly used at the end of combination spins and programs for a dramatic finish. To start the spin, I first step forward into a circular path. Since the amount of net torque is negligible, momentum is conserved, and according to the equation L equals RmV, as the radius of the circle decreases, the tangential velocity increases at constant mass. Therefore, to start spinning at a visible speed, the radius of the circle on which the skate travels decreases. Once the spin was centered, I started to bring my hands closer together. Doing so allowed me to decrease my moment of inertia, which expresses the body's tendency to resist circular motion. When mass is more closely distributed around the axis of rotation, the moment of inertia is reduced. This can be seen in the following demo in which two masses were attached to a stick. When placed at the ends, it was harder to rotate the stick than when they were placed closer to the center. This same concept is true in skating, and according to the second equation for calculating momentum, L equals I times omega, when the moment of inertia decreases, the angular velocity will increase when there is no net external torque. Looking at this other demo from bird's eye view will help to visually demonstrate how bringing one's hands closer together can help increase the rotational speed. When figure skaters perform jumps, they're essentially still spinning in this motion, but on a parabolic path as shown here. In conclusion, figure skating wouldn't be possible without several important physics concepts that exist.